So the question we posed in the last video at the end there was, is there a better way of implementing this heap so we can kind of know exactly where that empty spot is or where the last node is? And I want to highlight that there's a very important structure here in our heap because we know it's a complete tree. Because it's a complete tree, we know that every level is completely full except the last level, and everything is to the left on that last level. So one of the things that guarantees for us is that in this first level here, whoops, that didn't go. Oh no, we got this. This was just worked before I started recording. There we go. So in this first level here, there's going to be exactly one node. In the second level, there's exactly two. In the third level, there's exactly 4, and so on and so on. Now, I will say it's not always exactly 1, 2, or 4, and so on and so on. That last level might not be all the way full, but there's never more than that, and all the levels above you are going to be guaranteed to be full. And this structure, where each level is a power of 2, makes it really straightforward for us to, in some sense, represent this tree as an array. Now, it's not actually be super straightforward when you first see it, because it's really not obvious to try to represent a tree structure as an array. But this nice structure that the tree provides us gives us this really nice mapping. So what do I mean by that? Well, one thing we can do is in our array, we can start just laying out the tree in a flat manner. What I mean by that is we can kind of start by saying, okay, we'll put that first node in index 0, then put the second layer in indexes 1 and 2, and then put the third layer in the next 4 indices, and then put that final layer in the remaining indices. Each one of these kind of regions of the array is twice as long as the previous because these are powers of 2 here. Now, one of the powerful things here is that it's going to help us be able to index into this array because we're going to kind of know where to go. We'll come back to that in 1 second. Now, this array representation of the heap is, in some sense, an implementation detail. We're still going to think about this thing as represented as trees and nodes, but the way we're actually going to implement it is stored in an array and indices. So the reason we want to show you this is because this is actually the way everyone implements these heaps in the wild. They're really backed by array structures, but I promise you, this intuition that we have of it being a tree is not useless. Everything we've discussed about the tree is true, and the way you think about percolate up going and the way percolate down works. The only difference is the way we're going to actually implement that is moving things around in array indices. And we'll talk about why we want to represent that array in just a second. But I want to quickly show you, I have another slide with a bit of math on it, and the math isn't here to scare you, but it is trying to show you that there is a formula here. For any kind of value of interest in our tree representation of the heap, there's actually a simple, but maybe not understandable, formula to figure out where it is in the array. So for example, the minimum value is at index 0. That's why I have here. Peak min is just the array of 0. If you ever want to find the last node, well, it's just the size of the heap, the number of elements you stored in it. It's just the index minus 1 of that. So if this thing has, 12 values in it, then the last thing's going to be at index 11 because it starts at 0 indexed. How do you find the next open space? It's just one after that. It's just array of size. Now, the most clever one, and one that's really not clear, is for any index I, you can actually really simply find its left and right child. Its left child is going to be stored at index 2i plus 1, and its right child is going to be stored at 2i plus 2. I promise you, it's probably not clear why that's true. You're just going to have to believe me. That you can kind of calculate where that index is by just multiplying 2 times I plus 1 That's just going to give you the index. Let me show you an example to try to convince you. So let's look at, I don't know, this node here with the E. What index is E at? E is at index 4 in this array. Now, how do I figure out where its children are? Well, its left child will be at 2 times 4 plus 1. That's index 9. And its right child will be at 2 times I plus 2. That's index 10. And look at that. In this picture, J is the left child and K is the right child. This only is able to work because I know this is a complete tree. I know exactly where its nodes are going to be because I have all the previous levels filled out, which is a really, really clever trick that we can use here. Similarly, just like you can find the children of a node, you can find the parents of a node. You just use this formula I minus 1, divide by 2. And just to mention a subtle point, it's usually the case that maybe I minus 1 might be odd. We use integer division here, so you don't ever have to deal with floating point numbers or halves or things like that. Okay, I'm going to clear this, and I want to move on to the next slide. There we go. Now, one thing that's, if the array implementation already was a bit weird, one thing we're going to actually sometimes encourage is something even a bit weirder, which is if you actually start the array at index 1 instead of 0, it actually makes a lot of that math a lot simpler. So here's the exact same slide, but with putting the first value index 1, we essentially just leave a blank spot at index 0 and just fill in everything after that. And you can see here all the math is more or less the same, but there's less plus 1s and minus 1s. So the math just works out a bit better. And so we actually encourage you on your project to think about, how you can simplify your math by making the start index something like 1 instead, to simplify things. But that's a little bit more implementation detail on the project page. But this is just one weird trick. You're just gonna have to believe us that this math on the slide is correct, and depending on which index you're starting off, you'll use slightly different equations. So this slide and the slide before, depending on which index you decide to start from, is going to be super, super helpful when you think about implementing your project, because we're going to actually ask you to implement this array-based structure for the heap. And thinking about, okay, well, now I understand how this percolate up and percolate down work in the tree case. How do I map that to something that's actually like accessing indices of an array? And you'll find that these formulas are super, super useful. Now, what I want to talk a little bit about is the run times of this. Why did we go through all this trouble of actually implementing this as an array when we already went through all of Wednesday talking about this beautiful tree representation? I told you earlier that we are not going to improve the asymptotic runtime in the best or worst case. There's still going to be best case big theta of 1, and in the worst case big theta of log n. You still, worst case, might have to percolate that node up. And remember, when we think about the array implementation, percolating up the tree means moving it earlier and earlier in the indices, but it's the same idea. It's just kind of swapping those around, swapping around nodes at indices. So why did we go through all of this trouble to implement it like this if it wasn't actually going to make this asymptotically faster? So the first reason is that we kind of talked about this last week, but these constant factors that big O notation hide sometimes do matter in the real world. Since we're using arrays here, this array access gives us a much faster usual lookup time in the memory system that we might be working in. So you might run into spatial locality because this array is going to be contiguous in memory, and so you might get caching benefits, which is really, really great. And because we know the height of the tree is going to be kind of shorter, this array isn't going to have to be super, super, super long. And so it's more likely that this system is going to be somewhat faster in terms of like real world runtimes, even if asymptotically they scale the same. So that's kind of the first reason, that arrays generally just tend to be faster. And in this really nice and pretty complete tree case, it's really nice for us to represent that as an array. Whereas, if you had some arbitrary tree, the array gets a little bit trickier because you don't quite know where all the nodes are. You might have a bunch of empty spaces, and it's not quite clear what benefit we get there. Now, one other thing that we didn't quite talk about in that last example was that there tends to be a slightly different in practice case for these heaps than kind of the worst case. So remember, the worst case is like, here's this set of inputs you can give, and this is the worst thing that could possibly happen. But sometimes it's generally kind of hard for you to construct that worst case in real life. And usually you might just use it in some arbitrary application, not really thinking about what's the precise order I'm adding things in. And are you going to get that log n every single time? It turns out that in practice, adding values to this heap structure can usually be done much faster than that whole log n. The reason behind this is because this tree is complete, the majority of the nodes are leaf nodes, or in the last 2 levels. Why is that? Well, with this doubling trick of doubling the number of nodes available at each level, right? There's twice as many children each time. At the last level, there are twice as many nodes as the whole tree above it. So most of the nodes are low down in the tree. And because of that, and if you're building up this heap, it's usually the case that when you add a new node at the bottom, it's not going to percolate up very far, generally. It's still, in the worst case, going to have to go up all the way. But in practice, we generally see they only go up 1 or 2 levels each time before they're finding their resting spot. So in a lot of cases, we actually find that in practice, that percolate up is generally more like constant time. Again, not the same as the worst case. The worst case is definitely log n. But in practice, it tends to be closer to that constant. Now, why does that matter in the array implementation? Well, with the array implementation, remember for adding, we had to go find that last node to add it in at the right spot and then percolate up. Well, now that we have the array implementation, we can instantly get to that last index. We don't have to search the whole tree or search the height of the tree for the next available spot. And so now our add in practice could be a bit closer to that theta of 1. Now, the last reason is not necessarily a performance reason, like a faster memory or faster speed or less memory, but it's really like a developer standpoint. It is way simpler to implement this thing with an array than it is with trees. That might not be clear now because you're like, well, this array implementation is weird, but I already gave you all the math for figuring out, okay, if I'm at an index, where are its children? Really, trying to swap something is really simple as just swapping 2 values at an index or their indices. But implementing things with the tree, well, that goes back to Project Zero, where we made you write those binary tree functions and you had to like move nodes around it. That was such a pain. With the array code, it tends to be a lot more straightforward in terms of doing these heap operations, which is just much, much nicer. Now, oh, whoops, I went ahead too far. Now, one last thing I want to talk about is we've kind of, in some sense, maybe given you a false dichotomy here. When we introduce this idea of a heap, you might be kind of setting up Avl trees and heaps to fight each other. And I want to highlight they're not really fighting each other in the same ring. They're really good for different situations. So, for example, heaps, either the tree implementation or the array implementation, they're optimized for this case of a priority queue ADT, where the operations you really care about are finding the minimum value or removing the minimum value and adding in new values such that it's easy to remove the min. So the remove min operation for heaps tends to have constant factors that are better than Avl trees, but asymptotically they're the same. And that add, as I just argued with that array implementation, generally gets you that like sweet theta of 1 runtime. Usually has very few swaps. And so this heap structure does a really good job when you're trying to use it for a priority queue. Avl trees, they don't shine in the priority queue context, but they're great in the context of maps or sets. Avl trees are fantastic for making sure that the runtime of finding any node in the tree, any value in the tree, is worst case log n, where that's not the case for the heap. The heap is optimized for finding the minimum value. It doesn't really give you any guarantees about finding some arbitrary value. So, unlike the heap example, which would have to do a linear scan over that whole data to find a particular value, Avl trees are guaranteed to find anything in log time. And so they just have different priorities. I wouldn't say that one's better than worse than the other. They just kind of work in different contexts. Now, in the next video, I'm going to show you kind of a really clever usage of heaps that's really not clear from what we're talking about, what we've seen so far, which is building up a heap when you already have a bunch of data in some other structure like a list. But we're going to get that there in the next video. In this one, we really just talked about kind of how do we implement these things with arrays and kind of comparing them to Avl trees.